Okay. Hello, everyone. I hope you're enjoying your mid-sem break so far. I definitely was until about 30 minutes ago when I had recorded this whole tutorial and then irreversibly overrode it. So I'm going to be recording it again. That's okay. Today, I will be covering the week 9 tutorial problems relating to dependence and the introduction to copulas. We looked at questions 1 through 3 in class last week already. So I'm going to focus on questions 4 through 7 now. And if I have time at the end, I will quickly go over question 3 again, just like detailing the really main important concept parts that will be important. But that's only if I have time, so no promises. We'll see how I go. Okay, so let's jump straight into it today. All right, so question 4. So as an insurer, we have the opportunity to insure two risks, X1 and X2, that have identical distribution. We're given this exponential utility function and this initial wealth of 2. So part A is asking us to use the standard deviation principle with 30% loading and calculate the premium pi charged on each risk individually. Okay, so part A, I'm going to denote the premium as pi of x. Right, so I'm also just going to say the risks, as I already said in words, but I'm just going to write it as well. The risks are identical, so share the same premium. Right, and that is what we're denoting pi of x. Okay, so our standard deviation principle says the premium should equal the expected value plus alpha times the standard deviation. So in this case, since it's a Bernoulli, the expected value is just p, which is 0.05, plus alpha, which was 30%, times the standard deviation, which should be root p times 1 minus p. So root 0.05 times 0.95. Plug that in your calculator, and you'll get 0.1154 to 4 decimal places. Okay, and then I'm also going to store that value in my calculator. I'm going to store it as A. Store it as whatever letter you like, but it is going to be helpful later on when we need to use that value again. Okay, but that's it for part A. So that's our premium for each individual risk. Now part B, assuming that both risks are independent, if we charge the premium from part 1 to both risks, so charging 2 times that premium in total, what is our expected utility when we insure both risks? And from that, we need to ask, is that advantageous to us as the insurer? So this is a case of us comparing the utility of not taking the risks to the expected utility we have when we do take on the risk. So we need to calculate both of those. All right, so firstly, our utility by not taking the risks. Right, that's just going to be equal to U of W, right? Our initial wealth, which was 2. So that's equal to negative e to the negative 2. Plug that in your calculator, negative 0.1353. Okay, and then the expected utility of taking on the risks so remember, that is going to be the expected value of the utility of our initial wealth plus the premium that we earn. So this is just 2 times the premium we found in the previous question. And then take away any claim payouts we have to make, which are random at the moment, right? So then all we're going to do to compute this is sub in our expression for the utility at this point. So negative e to the negative all of this stuff. So it'd be negative w minus 2 pi of x, and then plus x1 plus x2. So now this part with the w and the pi of x, that's just a constant, so we can pull that out of the expectation. And then since x1 and x2 are independent, we can separate those into their own expectations. So our next line is going to be negative e to the negative w minus 2 pi x, and then the expected value of e to the x1 times the expected value of e to the x2. And then the nice thing we'll note about this is this expression for both of them, right, is just the MGF evaluated at 1. And since, again, x1 and x2 are identical, these expressions are going to be the exact same. So now, subbing in some of our values, so w is 2. I'm going to use a to denote pi of x since I stored my value in a before. And then we can get the MGF of these Bernoullis by just looking at our formula sheet, go to the binomial part, and just use the n equals 1 version of that. And you will get this. And then we're just going to square that since it occurs twice. Or you could also think x1 plus x2. So the sum of two Bernoullis becomes a binomial with n equals 2. Right? Same thing. So again, sub all that into your calculator. At the end of the day, you'll get this. And then all we're going to do is compare. So this is our expected utility under taking the risks versus the utility of not taking the risks. And we see that our expected utility actually exceeds, so it's bigger than utility of not taking on the risks. So therefore, we're just going to say it's advantageous for us to take on those risks. Right? At least under a utility perspective, it's advantageous. Okay, on to part 3, or part C. Now, assuming that x1 and x2 are no longer independent, but rather share this joint distribution here with those probabilities, we want to find the correlation between x1 and x2. Okay, so part C, the correlation between x1 and x2 is just equal to the covariance of those two, right, divided by their standard deviations. Now, just for simplicity, since x1 and x2 again, they're independent, identically distributed, sorry. So that means their standard deviations are going to be the same. So standard deviation times standard deviation, we can just write it as the variance of one of them. I'm just going to pick x1. Right? And that's just because they are identically distributed. So now we just need to calculate the covariance and the variance. So the covariance of x1, x2, to calculate this, we are going to appeal to the definition of covariance, which after simplifying says it's equal to the expected value of x1 times x2 minus the expected value of x1 times by the expected value of x2. Okay, so the only hard part that comes from this now is calculating this expected value of x1 times x2. But to do that, all you need to remember is the definition of expectation just tells us that it's the summation, right, in a discrete case, of x1, x2 times by the probability of whatever two values that are occurring, and we sum that over all the different possible combinations, right? So referring to our table of values here, it'll be 0 times the probability that that occurs, plus 1 times the probability that occurs, and so on, right, for those four combinations. That's just 0 times 0.94, plus 1 times 1 times 0.04, plus 1 times 0 times 0.01, and then plus 0 times 1 times 0.01, and then minus the expected value of x1 times the expected value of x2, which are both just 0.05. Right. Sub that in your calculator. You'll see that those three terms are 0 anyway. So it's really just 0.04 minus 0.05 squared. You'll get 0.0375. And then we just need to calculate the variance of x1, which is just going to be p times 1 minus p. All right, so we get 0.0475. Thus, we can sub in our values to get the correlation. All right, and we get that. So almost 0.8. And then, of course, when you do these sort of questions, you can do a little sense check, make sure the answer you get for the correlation lays between -1 and 1. And then if it does, you know that it's at least plausible what you got. Hopefully, it'll be right. If you get something outside of, so want something bigger than 1, something less than -1, then you know for sure you've done something wrong. You can go back and see maybe what you did. Okay, but that's our correlation. So then part D, in the case of correlated risks, what is our new expected utility? And then what do we make of this? So we just need to make a little comment, maybe comparing what we got in part B and what we get in part D once we do that. Okay, so part D is basically the same start. So the expected utility, so our initial wealth plus the premium we get minus any claims. So minus x1, minus x2. The only thing I'll note is that we're assuming that we're charging the same premium. So this premium here is still 2 times that answer we got in part A. Okay. So again, this is just going to be the expected value of negative e to the negative w minus 2 pi x plus x1 plus x2. We're going to pull the constants out the front again. However, we can no longer split the expectation into the x1 and x2 parts, right? Since they're not independent anymore. So we need to keep them together under the same expectation as e to the x1 plus x2. You can no longer separate them. So now to compute this, again, we're basically just going to appeal to the definition of expected value. We're going to look at all the combinations of x1 plus x2 and their associated probability of what can happen and just make sure we exponentiate it. So for example, x1 plus x2 can either be 0, 1, or 2, right? If it equals a 0, that means x1 and x2 are both 0, and that occurs with probability 0.94. So we're going to get e to the 0 with 0.94 probability. x1 plus x2 being 1, either x1 could be 1, x2 could be 0, or x1 could be 0, x2 could be 1. So that corresponds to these two. So that occurs with probability 0.02. So that'll be e to the 1 times 0.02. And then for the last one, will just be e squared times 0.04, right? The probability that they're both equal to 1. So again, start that in your calculator. You'll get this answer, which you'll now notice, so 1386 negative is smaller than our utility by not taking on the risks. Right, so it's now smaller. So it's no longer advantageous for us to insure those risks. Okay, and that makes sense, right? Since the risks are positively correlated, that means if one of them was equal to 1, then it's more likely the other one is also going to be equal to 1. So it's more likely the insurer is going to have to pay out more claims, right? That's the main idea. And this also ties back to the fact that we're charging the same premium as we did in the independent case. So of course, our expected utility is going to be lower than it was in the independent case. And it just so happens that it's also lower than the utility you get without insuring the risks at all. So in fact, just overall, it's no longer worth insuring those risks. Okay? At least, again, under our utility perspective. Okay, that's everything for question 4. So now on to question 5. We're saying let x and y have the same density, so 2x or 2y, and they are both bounded between 0 and 1. We're given their joint CDF as this thing, and our goal is to compute lambda u, so the upper tail dependence of the two. And for practice, we're going to use the definition of upper tail dependence rather than our Copulas shortcut, but I'm also going to show you how the Copulas shortcut just naturally pops up when we do it by the definition anyway, which is quite interesting, in my opinion, at least. Okay, so to start, we're going to need the marginal CDS and their inverses. So given the PDF is 2x, right, if we integrate that, and if you do it properly, your PDF is just x squared. And then if you take the inverse of that, right, since it's on positive x, the inverse would just be root x. So now, instead of jumping straight into lambda u equals the limit, blah, 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 we're just going to consider the actual stuff inside the limit that we're going to need to calculate. So what is the probability that y is bigger than some value? So we're going to call it inverse at u, given that x is also greater than this value, right? So it's just like the uth percentile or quantile. Okay, the first thing we're going to do is use our definition of conditional probability to rewrite this as the probability of intersection over the probability of the condition. Okay, and immediately we run into a bit of trouble here because obviously this top thing is not in a computable form currently by hand, right? The CDF needs less than or equal to, not greater than. So we need to figure out a way to rewrite this in terms of CDFs instead. And the way we're going to do that is appeal to this little diagram here. The first thing I'll note is this U I'm using to just represent the quantile. So this U really should be the inverse CDF of U or at U. But I'm just using U just for simplicity. So hopefully you guys agree that this thing that we're interested in, the probability that they're both bigger than their youth quantiles, is this really top right corner, right? The probability that x and y are both larger than that value. I'll also note that I've stopped these at 1 since x and y are both bounded at 1, right? So this could go on for longer, but since x and y are both bounded at 1, we can stop it at 1. So now, what I'm going to do is, so we want to try and think about the complement, right? That's usually what we try and do. So we're interested in this area, so all of this stuff. So maybe something we could do is, okay, if I take this block, so the probability that x is less than or equal to 1, which is 1, and the probability that y is less than or equal to u, then we can take the corresponding block for the top part up here. Again, this is now the probability that y is less than or equal to 1, which is 1, and the probability that x is less than or equal to u. If I add those together, that'll give me one lot of this upper part, one lot of this upper part, but then two lots of this main body part, right? So then I just need to take away one lot of this where x and y are both less than or equal to u. So overall, what we could say, maybe, is this red part is equal to 1 minus. So we add in one blue part, we add in one yellow part, and then we take away one green part, right? One of the big middle parts. And that should give us that red part. So I'll give you a second to maybe pause the video, have a think if it doesn't make sense immediately. But that is what we're going to get. So once we have that, what we're going to do is rewrite this red highlight bit exactly using that stuff that we just talked about. So 1 minus the probability that y is less than or equal to, so remember I used u, but it's really f inverse at u, and the probability that x is less than or equal to 1, minus the probability that y is less than or equal to 1, and x is less than or equal to inverse f at u. And then since we've got a minus minus, that green part's going to become a plus. So it's going to be plus the probability that x is less than or equal to this inverse, and y is less than or equal to this inverse. And then that's all over 1 minus the probability that x is less than or equal to f inverse at u. All right. Now it's going to start simplifying pretty nicely. So this first term here, since x being less than or equal to 1 is guaranteed, this first term is really just the CDF for y being less than or equal to this value. Right, so that's just going to be 1 minus f of y, f inverse u. And then same thing for this second term. Y is guaranteed to be less than or equal to 1. So really, this second term is just the CDF of x, being less than or equal to that value. So f of x, f inverse of u. And then this last term is going to be the joint CDF of those two. Right? Both at the same value there. And then that's all over 1 minus the CDF of x at that point u. So if you apply a function and then its inverse inside, that's just going to undo itself and you're just going to get the argument out. So you're going to get 1 minus u here, and then still this CDF, this joint CDF. And then on the bottom also, you're going to get 1 minus u. So next, we're going to get 1 minus 2u plus f of x, y. I'm just going to plug in the actual values now as well. So f inverse of u should just be root u, and 1 minus u on the bottom. Now this is where the Copula shortcut basically comes from. So if you remember our alternate definition is 1 minus 2u plus c of u over 1 minus u. Already you can see we've got the 1 minus 2u and the 1 minus u. So then we can just use Sklar's theorem to see that the copula at uu is actually the exact same thing as this part in the previous line. Right? If you can't remember, go back to your lecture notes, have a look. You'll see that that was one of the definitions we looked at. The joint CDF at these quantile arguments is just equal to the copula at those quantiles. That's pretty interesting. So that's where it comes from. So it's pretty easy, right? As soon as you understand this diagram and where those probabilities come from, And it's also, I guess, not too hard to just memorize, I think, but up to you. Okay, to save some writing space, I'm going to compute this CDF argument over here to the left. All right, so since we're subbing in root u for both x and y, right, root u squared, that's just going to come u squared on top. Then 1 minus u on the bottom, so 1 minus u squared. So overall, it's going to be equal to u squared over 1 minus u squared. Then I'm just going to expand at the bottom and simplify it a little bit before we keep going. It'll just make our lives a little easier. So those ones will cancel. And then you can see every term here has a u, so we can cancel a u. So overall, we just get this u over 2 minus u for now. So sub that in. And then I'm just going to combine the denominators on top. So I'm going to multiply 2 minus u to both terms over here. And then that 2 minus u will make its way down to the bottom. Then I'm going to expand the top. Hopefully I don't make a mistake this time. And then I'm also going to reverse the order of the bottom. So I mean like 1 minus u, make it u minus 1. Because u minus 1 is like -1 times 1 minus u, right? And then since I'm pulling a -1 out of both, it'll just be a 1 at the end of the day. Hopefully that made sense. Okay, now on top, you can see we've got 2u squared, minus 4u, minus u plus u cancel, and then plus 2. So I'm going to pull a factor of 2 out. We'll be left with u squared minus 2u plus 1. Hopefully you guys can see where this is going. That numerator is a perfect square for u minus 1. So that's going to enable us to cancel a factor of u minus 1, top and bottom. And we're left with that expression. So now, the upper tail dependence is just going to be equal to the limit as u approaches 1 from below of this expression, which we can just sub 1 directly into. Right, that'll just be equal to 0. So, i.e., there is no upper tail dependence. Okay, and remember, like all measures of like correlation and stuff, if it equals 0, that doesn't necessarily mean that they're independent. It just means that specific measure of dependence is 0. So that it's no upper tail dependence. That doesn't mean they're independent in general. They might still be dependent. Okay. In fact, you could show that since our joint CDF isn't just the product of the marginals, right? That means they're dependent anyway as well. Okay. So now on to question 6. Consider two standard normals, x and y, with a copula given by this nice long expression, where theta is greater than or equal to 1. It's just some parameter. Part A, we're going to show that if theta equals 1, then x and y are independent. So if you remember, we had a special copula formula for independence that was just the copula, or C of u1, u2, is equal to u1 times u2. So it's just the product of the inputs, right? Which is very similar to like your definition of independent densities, right? It's just the product of the densities or the product of the CDFs. So for part A, I'm just going to say when theta equals 1, C of u1, u2 basically I'm just going to write out the formula and sub in theta is 1. So nothing special at the moment, just writing it out. Okay. So now, just, I guess you could call it simplifying, but not really. And then expanding this bracket. Okay, so let's see. Simplifying a little bit more inside here. We're going to have 1 plus 1 minus 1. So we're just going to have 1. We've got a minus u1 minus u1, but there's a negative there as well, so it'll become a plus. So there's no u1. And then similarly, minus u2 minus minus u2, so no u2s. And then minus u1 times u2. So we're just left with this. And then once we expand this final bracket, 1 minus 1 will disappear. Minus minus u1, u2 becomes u1, u2, which is exactly what we wanted, right? Which is the independence copula. So that implies that x and y are independent. Okay. On to part B. Find the upper tail dependence of x and y. Since we have the copula this time, we are going to use that shortcut. So using the shortcut, formula, going to see lambda u. So our limit as u goes to 1 from below is 1 minus 2u plus c of uu all over 1 minus u. Next line, I'm just going to substitute our expression for the copula. So that's plus 1 minus, and then a big bracket, 1 minus u to the theta, plus 1 minus u to the theta, minus 1 minus u to the theta, times 1 minus u to the theta, big bracket, all to the 1 over theta. And then divide all of that by 1 minus u. Now, 1 plus 1 on the top there, that'll just become 2 minus 2u. Then inside the bracket here, you can see there's a 1 minus u to the theta in every term. So I'm going to pull one of those out. Then inside here, we've got 2 lots of that. So we'll have 2, and then we've got another factor of 1 minus u to the theta there. All right. Next, we're going to pull a 2 at the front of this first little bit. So we'll get 1 minus u. And then you can see here, since we've got the product of 2 things all to this power, we can separate those into separate powers. So it'll be 1 minus u to the theta to the 1 over theta, which would just be 1 minus u, right? Those thetas will cancel. And then we've got the rest. So hopefully you guys see where this is going. We've got a 1 minus u common to every single term. So we can cancel that out. And then just writing everything else out. We can sub u equals 1 directly into this. This term here will disappear. So at the end of the day, it's just 2 minus 2 to the 1 over theta. Okay, and that is our upper tail dependence for any value of theta that we use. Right, you'll see if theta was 1, this thing would equal 0, right? Since when theta was 1, they were independent, that makes sense. And the only other thing I'm going to note is that as theta increases, right, this part goes to 0. So the upper tail dependence increases as theta increases. Okay, I'm just going to note that might be helpful for the next part. Now on to part C. If theta is equal to 10, find the probability that both x and y exceed their 99th percentile. Compare this probability to the independent case and comment on the difference. So for this, firstly, I want to recall Sklar's theorem again, just saying the joint CDF is equal to the copula at marginals. Right. Okay, so then, like in question 5, because we've already given ourselves a nice formula for this, right? We have the probability that x is bigger than its 99th percentile and y is bigger than its 99th percentile. That should just be equal to 1 minus 2u and then plus the joint CDF, which we don't have, but we have the copula. So we're going to make use of Sklar's theorem there. Right, at these arguments, so the 99th percentiles. So using Sklar's theorem now, we'll see if we sub, so this inverse into our x value, right? The inverse and the CDF is going to cancel each other out. So we'll just be left with the copula 0.99, 0.99. And then we're just going to sub that in to our formula. Right, so 1 minus u to the theta plus 1 minus u to the theta minus 1 minus u to the theta, and then again, so to the 20 over all to the power of 1 over theta. Plug that into your calculator. You should get this. I'm going to do it myself just to make sure I haven't made a mistake. I got the same thing. So we're all good. Now I've given my answer to 4 significant figures, just because it's probably a little bit better than 4 decimal places since there's so many zeros in this case. Just a side note for accuracy. Okay, so that is our dependence probability. So now if independent, probability that x is greater than its 99th percentile and y is bigger than its 99th percentile, we should just be able to break those off into their individual ones. Right, and then hopefully you agree that each of those is just 0.01. So therefore, just having that in 0.0001. That's our probability under independence. So now comparing these two values, you'll actually notice that the value we get under dependence is almost 100 times bigger than the value we get under independence. Right, and that perfectly matches this kind of conclusion we made in the previous part. As theta gets bigger, the upper tail dependence increases. So the probability that they are both in their upper tails becomes a lot larger, right, versus the independence case. If you're not sure how the upper tail dependence here correlates with this probability being almost 100 times bigger than the independence case, Gilly did respond to a question on discussion forum recently about it. I would recommend giving it a read because it basically explains it really well. But for now, I'm just going to say that this is much, emphasis on much, lower than the theta equals 10 case. If you want your answer to be even better, right, I would have added in like almost 100 times lower or something like that. Okay, and then explain why, which is the stuff I was just talking about, the upper tail dependence, blah, blah, blah. Okay, and then on to our last question for today, question 7. Let x1 up to xk be a set of random variables admitting a certain copula C. Consider our transformed random variables x1 star up to xk star, where all of the A functions are strictly increasing continuous functions. Okay, and the goal is to show that these transformed random variables admit the same copula as our original random variables. Okay, so if our x's were continuous, then remember that the copula will be unique. So all we're trying to say is that if we take these original random variables with their unique copula they have attached to them, we apply a bunch of strictly increasing transformations. They don't all have to be the same. They can be different as long as they're strictly increasing. Then the copula of these new random variables is going to be the exact same. So the dependent structure hasn't changed at all. Okay, so to start, I'm just going to define a couple things. So let x tilde be, or let x tilde have the copula given by C x tilde. Let A1 up to AK be strictly increasing continuous functions. Okay, since they're strictly increasing, it means they're going to have well-defined inverses. That I'm just going to name normally A1 to the -1 up to AK to the -1. Okay, then just quickly, I'm going to say that the CDF of any X star, so any from, so I guess I should denote these I's, right? That's the probability that AI big Xi is less than or equal to little xi. If we take the inverse of both sides, we get big Xi is less than or equal to the inverse at that point. And that is just the CDF of our original Xi at this new point here, right? So that is going to help us a lot later on. And this result holds for I 1 up to k, right? So now what we're going to do is say Bias-Glass theorem. We're going to define our copula for our transformed random variables. So x star tilde. When we plug in our marginals, so x1 up to k, xk. Remember, this should be equal to the joint CDF. So f of x star tilde, denoting our joint of x1 up to xk. Then I'm going to rewrite this as a probability. So the probability that, so we could say, undo button works, x1 star is less than or equal to x1, all the way up to xk star less than or equal to xk. But x1 star is just equal to a1 of x1. Okay, and then we're going to take the inverse on every single one. So it'll become big x1 less than or equal to a1 inverse of x1, all the way up to big xk less than or equal to ak inverse of xk. And now this has suddenly become the joint CDF of our original x's at these new arguments involving the a's, right? So this is going to become f of x tilde, so no more star, of a1 inverse x1 up to ak inverse xk. And now we can use Sklar's theorem again. So remember, by Sklar's theorem, the joint CDF at whatever argument is equal to the copula of that joint CDF, or of that joint, set of random variables, of the marginal CDFs evaluated at those arguments we had on the right. So all we're going to do is we're going to rewrite, C of x tilde. But now that's going to be, so f1. So here, f1, but this argument, instead of it being x1, it's just going to be the first argument of our joint CDF, which was this a1 inverse of x1. So like that, right? And that's going to be the same for all of them. So all the way up to k, a lot of brackets. Now, if we go back to what we did at the start, we've got the CDF of the original thing at the inverse of a x1. If we went up here, that's exactly what we've got here. And that's just equal to the CDF of our transformed random variable at x. So this is actually just equal to C of x of our transformed random variable x star at x1, all the way up to x star k of xk. Right, and I guess in that previous line, I should write x1 and xk. So let's look at what we've got. On the left-hand side at the very start, we had the copula of our transformed random variable at all these arguments. And what we've arrived at is that that has to be equal to the copula of our original random variables, just x, but it's at the exact same set of arguments, right? The only way those two things can be equal is if those two copulas are the same thing. So we've shown that the copula for x star is the same as the copula for x, right? So that just means they admit the same copula. So we're just going to say this shows that x star tilde admits the same copula as x tilde, right? Which implies that the copula is invariant under strictly increasing continuous transformations. Right? I can't be bothered writing out all the words. Okay, which is a very cool result. All right, I think I have time to quickly mention question 3 again. So I know, again, you did it in class, but it's a very important question, the ideas. So I just want to mention it at least. So if you're comfortable with it, feel free to stop the video now. Thank you for watching. Otherwise, let's have a quick chat about it. So question 3, we've got a population of elves. As is well known, allegedly at least, elves cannot die of old age, only in accidents or in combat. So it's reasonable that under normal circumstances, their lifetimes are memoryless or exponential. So on the eve of a battle, we've got two elves, Elrond and Legolas, and they have these two lifetimes, T1 and T2, given by these products of random variables. So we say B is going to be a Bernoulli P star. B1 and B2 are just Bernoulli P's. X1 and X1 are exponential with lambdas. Okay, we note that they are all independent random variables. However, obviously T1 and T2 are not independent since they both share the same B, so they can't be independent. And then there's a little bit more context here. We could interpret B as a possible event that can kill both of them simultaneously, whereas B1 and B2 are events that kill just one of them, right? And then X1 and X2 would be like just their normal lifetime otherwise. Okay, so our goal is to find the correlation between their two lifetimes. Okay, so the correlation between T1 and T2. So in order to do that, again, like we did near the start, note that B1 and B2 are the same distribution, right? They're identically distributed, same with X1 and X2. So the variance of these two things, T1 and T2, are going to be the same, right? Since B, B1, and X1 all share the same distribution as B, B2, X2 in that order, right? So note variance of T1 equals variance of T2, and that's just going to help us when we write the correlation is equal to the covariance between the two over the standard deviations, which will just become the variance of one of them. Okay, so now again, like before, we just need to find out what those two values, the covariance and the variance, are. So to do the covariance, we again appeal to the definition of covariance. So it's going to be the expected value of T1 times T2 minus expected value T1 minus expected value T2. The first thing we're going to do is just replace T1 and T2 with their definition. So the B, B1, X1, B2, X2s, okay, all of that stuff. So shoving all of that into our expectation, we'll get these. And then same over here, we'll get those. And then what we're going to get inside this first one, right, you'll see we're going to get a B squared, B1, B2, X1, X2. Hopefully you agree. If B is independent of those, then B squared is also going to be independent. So since all of these random variables are independent of each other, we can split them all into their own individual expectations. So that'll give us the expectation of B squared, which I've got over here, expectation B1, X1, B2, X2, right? So that's this first part. Then the next part, again, basically the exact same thing. We can split this into expectation of B, expectation of B1, expectation of X1, and then similar with the second one. And at the end of that, right, we're going to get expectation of B all squared, right? So not the expectation of B squared, expectation of B all squared. So that gives us this next line, since these other four terms were constant to both of those. So then we've just pulled out these other B terms, which you'll also notice nicely is just the variance of B. So all we need to do then is just sub in all of those things. Since we've now managed to split all of that into just individual expectations and variances, we can just look at formula sheet, or if you remember the formulas, just sub them straight in and you'll get your covariance. Okay, and then very similar for the variance of T1, we're going to use the definition of variance. So the expectation of the random variable squared minus the expectation of the random variable all squared. And again, sub in the definition of T1. So just in this first one, remember that square will go to everything. And again, if the original random variables are independent, their squared's also going to be independent. So we can split each of those into separate expectations. We can do the same thing with this next one, just remembering that squared will stay on the outside and go to all of them. And again, we can just calculate all of these values. If you don't remember, like what the second moment of a Bernoulli is, you can get it from the variance, or you can think about the definition of expectation again. I'll leave it to you to figure out, but it's just equal to these. Similar with the second moment of an exponential, you can get that from your formula sheet. And then these are all the first moments from this right term. And again, just simplify it, get a nice answer, and then back at the top, sub in everything you got, do some simplifying, and you'll get this expression as your correlation between the two. In this case, that's all the question asks us to do. But the only other thing I would note is that it's very possible in a test or the final exam or something that will ask you to maybe interpret the effect that P has on the covariance, right? In which case, I'd probably recommend, say, making this a function of P, differentiate it, and show that it's an increasing or a decreasing function of P, and just explain what that means, right? As P increases, the correlation increases, and maybe explain why that might be the case, or for P star, something like that. Okay, hopefully that makes sense. That's everything I wanted to go over today. Thank you very much if you watched the whole video. If you have any questions, please let us know on the discussion forum. Otherwise, I hope you enjoy the rest of your mid-semester break. Study hard for the test, and I'll look forward to seeing those from my class back in week 10. That's everything from me. See you guys.